Parametrized curves are going to get us very quickly to calculus with vectors by looking at derivatives of such curves and thinking in terms of rates of change. So let's say that we have a parametrized curve in three-dimensional space. Let me call it gamma, going from R to R3, where the input is time, and the outputs are the three coordinates, x of t, y of t, and z of t. Thinking of this as a vector, as a position vector, motivates us to say, hey, what happens when we take the derivative of this? That is, I just take x prime of t and y prime of t and z prime of t, the usual derivatives, stack them together as a vector. Let me call that gamma prime. Or I can think of this as the derivative of the position vector, the velocity vector, v. So the derivative takes me from r of t to v of t. If I differentiate again, I get a of t, the acceleration vector, the vector that consists of the second derivatives, x double prime, y double prime, z double prime. So we just compute derivatives, one coordinate at a time. Now, how do we think about these derivatives as vectors? How do we think about these geometrically? Well, the formal definition of the derivative of a vector-valued function makes sense. In arbitrary dimensions, the definition is exactly what you think. R prime of t is really the limit as h goes to 0 of r of t plus h minus r of t divided by h. But notice how in this definition, we're really using vector addition, or subtraction in this case, and scalar multiplication for vectors, that is multiplication by 1 over h, and taking a limit as h goes to 0. So you can really see this if you think about what is happening. When I take the difference between these 2 points, I get a vector. When I divide by h, that vector quantity in the limit grows, turns into this velocity vector, which we can now see is really tangent to the curve at the point at which you're taking the derivative. This is the important thing. The velocity vector has a direction that is tangent to the curve, and it has a magnitude which is encoding the speed at which you are moving along the curve. Remember, this is a parametrized curve. You're moving in a particular orientation, in a particular speed. The velocity vector, the derivative, encodes all that. Let's take a look at an example of velocity and acceleration vectors. If I'm given the curve gamma of t, which has components sine of t times cosine t, and cosine squared of t. Those are the x, y, and z coordinates. Then, how do I describe the position vector, the velocity vector, the acceleration vector as a function of time t? All right, well, the position vector is done. That's it. That's gamma of t. There you go. To get the velocity vector, we have to take the derivatives of these functions. Now, I want you to remember that the derivative of sine is cosine, etc., etc., etc. You're going to have to remember your product rule, your power rule for derivatives, all that basic stuff from single variable calculus. Go back and review that and verify that these are indeed the first and second derivatives of these trigonometric functions. But what I want to focus on is what do these mean? What do these look like? Well, in this case, the velocity vector is going to be tangent to the curve at the point at which you're taking the derivative. The acceleration vector is also going to be a vector that is based at that point, but it's not necessarily tangent to the curve. And in fact, if you look at how these vectors evolve as time increases, as you move along the curve, you can see the velocity vector always tangent to the curve. In this case, it kind of looks like the acceleration vector is maybe perpendicular to the velocity vector. I don't know. We could take a dot product and try to find out. But in general, both of these sets of vectors are going to evolve.